Good afternoon, folks. I'd like to finish up the chi-square, and there are a couple of things to mention here. First thing is that the mean of the chi-square distribution is equal to its degrees of freedom. And the variance of the chi-square distribution is equal to 2 times the degrees of freedom. Therefore, the standard deviation would be the square root of the variance. So if I have a chi-square with 8 degrees of freedom, its mean would equal 8, and its variance would be 2 times 8, which is 16, and the standard deviation would be rad 16, which is 4. So as the degrees of freedom get larger, these curves get more and more spread out because the standard deviation increases. So chi-square with 1 degree of freedom looks like this. This is chi-square 1 degree of freedom. Chi-square 2 degrees of freedom looks like this. And chi-square 8 degrees of freedom would look like that. You get the picture. The standard deviation keeps increasing. Okay, next I would like to talk about a normal theory method for comparing proportions. We have already talked about the chi-square test for homogeneity of proportions, and this will be an equivalent test, except it'll be a z-test. So I'd like to begin by creating a matrix which is 2 by 2. This normal theory method is only good for 2 populations and 2 proportions, comparison of 2 proportions. So let's begin. Normal theory method for comparison of proportions. It's only good for 2 by 2 matrix, i.e. you have 2 populations. So let's say that I have 2 drugs, drug A and drug B, and I take a sample of, say, 20 people who are given drug A, and it's the total, and let's say 160 people given drug B, and I would like to talk about the percentage of these 20 who experience insomnia. So insomnia, let's say 5 out of these 20 experience insomnia, and no insomnia, 15. And here's the total, 20. And in the sample from drug B, 80% experience insomnia, and not 80%, I'm sorry, 80 people experience insomnia, and the other 80 do not. Add across, you have if in total who experienced insomnia, and 95 did not out of 180 people. So let's call this X1. These are the number of quote-unquote successes in sample A, and this is N1 for sample A. The size of the sample is 20. And here X2 is 80. These are the people who did experience insomnia, so these are regarded as successes. And N2 is 160. And then this is the total of X1 plus X2, and this is N1 plus N2. Next, I talk about the sample proportion P1 hat. This is the this is the probability of successes in sample 1. So this would be X1 over N1, which is 5 over 20. And P2 hat is equal to X2 over N2, which is 80 over 160, which is 1/2. This one is 1/4. And then there's P tilde, which is the common proportion, meaning total insomniacs over grand total here. So this is X1 plus X2 over N1 plus N2, which is 85 over 180. And therefore its complement, Q tilde, is 1 minus P tilde, is equal to this 95 over 180. And by the way, Q1 hat would be the probability of failure, which is 15 over 20. And Q2 hat would be the probability of failure here, 80 over 160. So we are interested in seeing if these probabilities for insomnia are the same for these two drugs. Clearly they don't look the same. Here I have 1/4 as the probability of insomnia, and here I have 1/2 as the probability of insomnia. So it's kind of obvious that they're not the same. However, we're looking to demonstrate the normal theory method hypothesis testing. So let's begin. H0, P1 equals P2, saying that the two probabilities are the same, versus HA, P1 not equal to P2. Let's say I'm doing a two-sided test. These tests can be left-sided, right-sided, or two-sided. So P1 not equal to P2 indicates two-sided test. I immediately bring this P2 to the left side. So I have P1 minus P2 equals 0 versus P1 minus P2 not equal to 0. This number doesn't necessarily have to be 0. I could have it be a half, I could have it be an eighth, I could have it be a 16th, okay? And if it's not 0, then you would have to complete this entire procedure by hand, because the calculator would not be doing it for you. Okay, let's say that alpha is not provided. And so we will use alpha equals 0.05. That's the standard as usual. We will need a test statistic, Z0. So Z0, the test statistic, is created by taking the sample proportions P1 hat minus P2 hat. So I take the difference in the sample proportions minus P1 minus P2 obtained from the null hypothesis. So in my case today, this would be 0, divided by radical P tilde Q tilde radical 1 over n1 plus 1 over n2. I'm going to show you in detail how I arrived at these. This, of course, is the mean of p1 hat minus p2 hat, like the following. E of p1 hat minus p2 hat is equal to E of, let's replace p1 hat by x1 over n1 and p2 hat by x2 over n2. Now this 1 over n1 is a constant, so 1 over n1. E of x1, x1 is binomial. X is binomial with mean np and variance npq. So let's go somewhere and write this. E of x, where x is binomial, E of x is given by n times p, and variance of x is given by n times p times q. We know that. We know x is binomial because this is a bunch of Bernoulli trials where either you experience insomnia or you do not experience insomnia. So we have the right to use mu equals n times p and sigma squared equals n times p times q. So I'm back here. I pulled out the constant of 1 over n1 and I have E of x1, which is just n1 p1. And here I pull out the 1 over n2, so E of x2 is n2 p2. So this n cancels with this n, and that n cancels with that n, and I'm left with p1 minus p2. That's where this p1 minus p2 right here comes from. This is the mean of p1 hat minus p2 hat. Next, I'm interested in the standard deviation of p1 hat minus p2 hat. So standard deviation of p1 hat minus p2 hat, of course, is the square root of the variance of p1 hat minus p2 hat. So next, let me work on that one. So variance of p1 hat minus p2 hat is equal to the variance of p1 hat. P1 hat, of course, is x1 over n1 plus -1 squared. Remember, when you have a coefficient in front of the p2 hat, you have to pull out that coefficient and square it. So my -1 squared times the variance of p2 hat, variance of x2 over n2. I'm replacing p2 hat by x2 over n2 because that's what it is. Continue. So pull out this 1 over n1 constant, this coefficient, and square it because I'm interested in the variance of a constant times x. So here I get 1 over n1 squared, variance of x1, plus 1 over n2 squared, variance of x2. So 1 over n1 squared. Now the variance of x1 is right here, npq. So n1, p1, q1, plus 1 over squared, n2, p2, q2. One of these n2's cancels with that on the denominator, and one of these n1's cancels with, this n1 cancels with one of these n1's in the denominator. So finally I am left with P1